So let us now look at this from let's take a more concrete example. Let's just take a 3 variable function. Okay. So let us look at A2, A1 and A0. Okay. And I am going to say Y0, and let me look at two outputs, Y0 and Y1. Okay. So this obviously has 8 input combinations, 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Okay. And then we are going to say that Y0, as per the previous example, was 1 0 1 0 1 0 1 0. So that's what I said, that there are 1, 2, 3, 4. So of the 8 combinations, 4 of them are 1. So therefore you have 2 power 2 combinations. We have 2 power 3 input combinations, of which 2 power 2, 2 power n minus 1 combinations are going to give you a 1, and therefore you are going to have a minterm corresponding to each of these guys. Okay. So let me construct another example here, okay, where I am going to do the following, right. So let me do this. So this is 0 0, okay. I am going to have, let me just consider 1 1 1 0 0. Okay, these are my unknown outputs, right. Obviously, by looking at this truth table, it's not possible to just tell what the Boolean representation or the Boolean function is for the two variables y0 and y1. Okay, so let us go ahead and do this thing. Okay, the exercise here. So this one corresponds to, let me move that to the right a little bit. Okay, I'll move this to the right so that I have space. Okay, so what is my minterm that I am going to write here? Minterm. Okay, so we are going to write the minterms only for the ones, right. So what is this? This is basically A2 bar, A1 bar, A0 bar, right. Then you also have A2 bar, A1, because in this case, in both these cases, A1 happens to be, sorry, not in both these cases, just this case, A2 is 0, A1 is 1 and A0 is 0. So therefore it is A2 bar, A1, A0 bar, right. Similarly, if I consider the next one here, okay, it has to be A2, because A2 is 1 now. Then I have A1 bar and I have A0 bar. Okay, finally I am going to consider this case, which is basically A2, A1 and then A0 bar. Okay, so the function Y0 is going to now be the sum of products of these minterms. Okay, this is A2 bar, A1 bar, A0 bar plus OR, right. The plus means an OR is a sum of product A2 bar, A1, A0 bar, or A2, A1 bar, A0 bar, or A2, A1, A0 bar. Okay, so this is what we have. Now we can go ahead and try to do a Boolean simplification of this entire thing. So one first thing you notice here is this A0 bar is basically common to every term. So therefore I can pull that out. Okay, and then I have A2 bar, A1 bar plus A2 bar, A1 plus A2, A1 bar plus A2, A1, right. So here again we can go ahead and do the simplification, right? You consider these two terms and then you consider these two terms. In the first term, A2 bar is common, A2 bar into A1 bar plus A1 plus A2 into A1 bar plus A1, right? So, both cases there is A1 bar plus A, this we know reduces to 1, logic 1, right? So, therefore, this is equal to A0 bar into A2 bar plus A2. Now, this again we know is logic 1 and therefore, this is A0 bar. So, what we realize is we started off with some 4 minterms, sum of products and all that, and then we realized that Y0 is simply A0 bar. Actually, this is not very hard to recognize because all you have to do is look at A0 here, look at Y0 here, and you will see that the input A0 is just being complemented in all the cases, right? And therefore, just sometimes by inspecting the truth table also it is possible to tell that Y0 is just equal to A0 bar, right? It cannot depend on A1 or A2. Whatever the value 0 or 1 for A1 and A2, it's very evident that your output Y0 is simply going to be a logical inversion of the input A0, right? So, this is again very it comes out both from the formal Boolean simplification, sum of products terms and also by inspection, right. So, it is very useful by the way to sometimes inspect the truth table and just see is there a pattern that you are able to see, okay, because that will tell you what to expect, right. And then if you make a mistake in your derivation, in your Boolean simplification, you can catch that later if you have this kind of an intuitive approach, okay. So, let us now look at Y1, okay, we have the second input Y1, okay, and I am going to write the minterms, okay. I am not going to in this case also by the way it seems there are 4 zeros and 4 ones, okay, it just so happens to be that way, right. So, I am not going to right now I am not going to look for the pattern to figure out what Y1 might be, right, but let us just see what we get, okay. So, we are going to write the 4 minterms. For this first one it is basically going to be A2 bar, A1 and A0 bar, okay. Then I have the next one here, this is going to be A2 bar, A1, A0. Then this one is A2, A1 bar, A0 bar. And the last one here is, which is basically this combination, it is A2, A1 bar, A0. So, therefore, Y1 can be written as A2 bar, A1, A0 bar plus A2 bar, A1, A0, okay, or A2, A1 bar, A0 bar or A2, A1 bar, A0, right. And therefore, I can again look to simplify this expression here, right. So, let me take out these two terms, okay, A0 is common, likewise these two terms A0 bar is common and therefore, let me just write that out separately here. I can write this as A0 bar into A2 bar A1 plus A2 A1 bar. Okay, that's basically this term, right? Then I have this term to worry about, which I will again write as, I'll take A naught out from this. Again it's A2 bar A1 plus A2 A1 bar, right? Now it's very evident that I have this A2 bar A1 plus A2 A1 bar as a common term for both these both these terms here, common factor. So I can remove that A2 bar A1 plus A2 A1 bar into A naught bar plus A naught, and therefore this is simply going to be A2 bar A1 plus A2 A1 bar. Okay, so what we see now is the output Y1 simply depends only on A1 and A2. Okay, so here if you look at it, it seems it's not so obvious. I mean, if now that I tell you it's an XOR gate between A1 and A2, if you go back you will see this pattern, but sometimes it may not be that obvious, which is okay, right? You will not be able to always catch this pattern when you are trying to simplify these things, right? Okay, so now let us see. Okay, I have reduced this expression, right? I have done something to the truth table. I have expressed it as sum of products. Then I have expressed it, I have sort of done some Boolean simplification and all that, right? So now the question is, if I were to go ahead and implement this, right, using some logic gates, what are the minimum set of logic gates that I need in order to implement any function, right? So let us look at that particular idea. Okay, so minimum set of gates needed to implement any Boolean function, right? So if you look at, so first we will not go ahead and look at the Boolean simplification as such, right? Let's look at just this sum of products term that we wrote. Okay, essentially we have each minterm is a product of either the true or the complement form of every input. Okay, so what you see here is each minterm is now going to be an AND of something, right? So therefore it's very evident that the first gate that I need for each minterm is of course the AND gate, but before that each input I might need its true or complement form, right? So either the true version or the inverted version, right? And therefore I need an inverter, right? Now on the other hand, for the sum, right, this is a sum of product. For the product term, this is what we need. For the sum term, I simply need an OR gate. I need an OR gate, right? Now the point is, how many input OR gate? Well, and how many input AND gate? That depends on the number of input variables. So if I don't do any Boolean simplification, then each minterm is an AND gate of either the true or complement of the input, and it needs as many the NAND gate needs as many inputs as there are inputs to this system. So therefore, how many input NAND gate, right? the AND or the how many input AND gate, sorry, this has to be n input. Okay. On the other hand, the OR gate, okay, how many input OR gate do you need? It is basically uh, sort of as many as there are minterms, as many as there are ones in your output, right? This is without Boolean simplification. Again, I'd like to stress on that fact, right? So therefore, the OR gate, let's say M, not a M, I've used maybe uh, P input OR gate, right? So just like we had a 2 input, 3 input, you can have any input OR gate, right? What does the any input OR gate do? If any one input happens to be 1, the output will be 1. Likewise, an n input AND gate, only when all the inputs are 1, the output will be a 1, right? P input OR gate, where P is the number of ones in the truth table. So why are we discussing this? Because ultimately the aim is to start with some definition or some problem statement that we want, obtain the truth table and then implement that using some logic gates, because that is what we eventually want to do in a microprocessor. Let's say for example you want to implement an adder, multiplier or something like that, you got to start with the truth table, get the Boolean expression and then go ahead and implement these functions, right? So anyway, so if I now go ahead and look at the unsimplified implementation y0, okay, it is a2 bar, okay, let me copy this, yeah, right. So I have copied this. So how many AND gates do I need? So I need, first of all, each AND gate has to be an n input AND gate, right? And by the way, how many AND gates do I need? I need again as many as there are ones in the truth table. So I have P AND gates. Okay. So how will I go ahead and implement this? It's like this. You start, just to this is A2, A1, A0. The inverted versions are coming out nicely here on these other lines. So this is A2 bar, A1 bar and A0 bar. Okay. So if I want to implement Y0, I need how many AND gates? 1, 2, 3, 4, right? So I have 4 AND gates. Okay, 1, 2, 3, and I don't have space, so I may have to copy the whole thing and go to the next page. Okay, so let me do this. Okay, so I am now here. I have the 4th AND gate. Right. So now I have A2 bar, A1 bar and A0 bar. So I need to select these inputs. Okay. So I get, so this by the way I will call, I can, okay, I don't have to do that. The second AND gate has to have inputs A2 bar, A1, A0 bar, right? So therefore again A2 bar, A1 and A0 bar, right? Then I have the third AND gate, which basically is, no, sorry, this is wrong, because this has to come from A2. I need A2, A1 bar and A0 bar, okay? And then I have A2 again, A1 and then A0 bar, okay? So I have A2 bar, A1 bar, A0 bar, the first minterm, A2 bar, A1 and A0 bar, the second minterm, A2, A1 bar, A0 bar, the third minterm, A2, A1 and A0 bar, right? So now you take a big 4 input OR gate and go ahead and implement this. Right, so this is why not, okay? Now the point is that why are we even worried about all this Boolean simplification and stuff like that, right? It's very evident. Just look at this implementation of the unsimplified Boolean expression, right? We basically used 4 and 4 gates, okay? So till now and 3 gates actually. Okay, till now I was just referring to these gates as AND and OR gates without the input. So from now I will also indicate the number of inputs like this. This is an AND 3, this is an OR 4. Okay, because it has 4 inputs, the AND gate has 3. So I have 4 and 3 gates, okay, 3 inverters or NOT gate, okay, and 1 or 4 gate, right? So it's like 4 plus 3 plus 1, the number of resources, right, is I needed about 8 gates in, if I don't differentiate between inverter or and an OR gate in terms of their area or something like that, then I'm just going to say I need 8 gates, okay? But what you found is, based on the Boolean simplification, we found y naught was simply a naught bar, okay? So all you needed to do was to take a naught bar like this, and this is y naught, right? That's all it is. There is nothing else to be done, right? So actually y naught was implementable using just one NOT gate or one inverter. On the other hand, out here what we needed was something like 8 logic gates. Likewise, if you go back, right, and look at the other expression here, right, the y1 implementation, okay, what is the y1 implementation? Again there were 4 ones, okay, but with in different combinations. So each of them needed a 3 input AND gate, okay. So if you look at the number of resources needed to implement y1, okay, let me just maybe get that expression also here. I'll remove this, okay, I will just copy that. Okay. Yeah. So again here each minterm basically needs 1 and 3 gate. Okay. So therefore in order to, again let me move this to the left here. Okay, this is for y naught. To implement y1 in a similar manner, you need exactly the same thing, 4 and 3 gates. Okay, 3 inverters. Okay, and 1 or 4 gate. Now this or 4 could have become or 3 or 2 depending on the number of ones. So for example in both these cases we had constructed. So suppose I have y2 like this 0 0 0 0 1 1 0 0. Okay, 1 2 3 4 5. Yeah, suppose this were the case, then in order to implement y2, of course I would need the AND gates. Okay, three input AND gates I would need, because that is just depend on the number of inputs. But the number of OR gates I would have needed is 1 2 input OR gate. Okay, so that is for y2. Yeah. Now again we needed 8 gates here, but then the actual implementation was simply A1 into A2 bar plus A2 into A1 bar. Okay, the simplified expression is actually, if you were to just look at y2, what do I need? I basically have something like this. Okay, I'll just extend this. Yeah. Okay, so what do I have here? I have the simplified expression y1 is A2 A1 bar plus A2 bar A1, right. So the first minterm is going to be with A2, okay, and I have A1 bar, okay, and the second expression is going to be with A2 bar and A1. Okay, I just do this and then give it to a 2 input OR gate. So y1 is like this, this is OR 2, this is also AND 2 now. And 2. Okay, so this implementation needed 2 into AND 2 gates. Okay, and of course you needed 2 inverters. Okay, to get A2 bar and A1 bar, and it needed 1 2 input OR gate, OR 2 gate. Now it's very important to realize that the cost of using an OR 2 gate is going to be much lesser than using an OR 4 gate. Okay. Now if I consider another example, for example where I have like maybe 6 of those 8 outputs combinations happen to be a logic 1, I would need an OR 6 gate. Now the cost of using an OR 6 gate is much higher, okay, in terms of area, in terms of delay and other things which we will come to later. So there is a lot of value and benefit in trying to reduce this expression to even use gates with fewer number of inputs. Okay, so that's the overall motivation for why this Boolean simplification is very, very important, right? So what we have done effectively is we have reduced it to its simplest form, right? There is no further. Y equal to A naught bar is the simplest implementation. There is nothing else that you can do further, right? Y1 again is basically going to be A2 bar A1 plus A2 A1 bar. Again it is down to its simplest form. There is no further Boolean simplification possible. So we want to bring it down to this because that is what will allow us to implement it with least area, delay and power. All of this I will talk about later in terms of when I want to highlight delay and the other things, right?